Yes, sir, start.
Good afternoon, everyone. Well, I welcome you all for the GATE online training. Good afternoon, everyone. I welcome you all for the GATE online training program, day 17. Today, we have two sessions. The first session is on foundation engineering by Dr. S.K. Prasad. And the second session is between 3:45 to 5:15 p.m. related to air pollution. To begin with, I introduce today's speaker, Dr. S.K. Prasad sir. First of all, I would like to welcome today's speaker, Dr. S.K. Prasad sir.
Thank you.
Dr. S.K. Prasad sir is serving as head HOD and professor in the Department of Civil Engineering. He did his BE from SJCE College of Engineering, Mysuru, and did his MTech from IIT Kanpur, and his doctoral degree, obtained his doctoral degree from Tokyo University. He has been serving as reviewer for many international journals, and also he is an active member of many professional body. With this brief introduction, I hand over the session to today's speaker, Dr. S.K. Prasad sir. Over to you, sir.
Thank you, Professor Arjun. Very good afternoon, everybody. I'm extremely happy that, we are into the last day of GATE training, which we started on 23rd of last month. I'm very proud and happy about the performance of all my colleagues, including, mathematics, plus all civil engineering disciplines. We have covered over 50 hours of lecture, and I'm extremely happy that anybody who goes through all these 50 hours of lectures will surely be in a very comfortable position to take the next GATE examination, GATE 2021 examination in February. With this brief note, I go on to my presentation, and I request my colleagues to say that, my visuals are clear. Am I clear?
Clear.
Okay.
Yes, sir.
And audio is also okay?
Yes, sir. You're audible.
Okay. So once again, good afternoon, friends. So this is my second lecture on foundation engineering. If you remember, I gave the previous lecture on the 4th of this month, wherein I covered all these topics: subsurface investigation, theories of earth pressure, stability of slopes, and stress distribution in soils. Now, I'll be talking about a more important topic in geotechnical engineering, that is foundations. So we have both shallow and deep foundations, and also settlement analysis of shallow foundations. So this is a vast subject, and if you recollect what I had told in the previous lecture, lot of questions have come from shallow foundations area. So looking at that, looking at the importance in general of these topics, friends, I request you people to, listen to the lecture. And as I said in the last class, focus is not on giving the concept. Focus is more on cracking the GATE examination. So I don't have to mention the importance of foundations. So as you all know, this is the foundation which will hold the superstructure, which will be in direct contact with the soil below. The major objective of the foundation is to transfer all these forces from superstructure to the soil below in such a way that soil here is not affected. it does not experience failure, nor does it experience excessive settlement. Therefore, you will be keeping in check the soil here, which neither fails nor will experience, settlement. So I always say, we'll consider the two limit states, just like in case of concrete, limit state of serviceability and limit state of collapse. So one major objective of any civil engineer is that, the structure is founded on a stable ground, and the foundation is also as strong and as durable as possible. This is the most important organ of the structure, and hence it should be strong. It also should be founded on stable ground. And then, you always will have a question as to what location of the soil you should be interested in. So if this is the superstructure and if this is the foundation, soil just below the foundation is the one which is affected because of the stresses induced, due to the load from the superstructure. So the stresses in soil should be within limits. So how much soil you should consider? So normally, if B is the width of the foundation, maximum 2 times B should be the depth, 2 times B should be the width up to which you need to consider the effect. Beyond that, the effect of the loads from the superstructure into the neighboring soil will be negligible. And as on today, every structure will have to rest on ground. I do not know, in future we may be able to put them in air, but as of now, every structure has to rest on ground, which means these structures which carry all kinds of forces will be transferred to the soil below. That means, so we have to identify how much load, how much force soil can take before it fails, because that is very important to decide about the kind of foundation for any structure. Well, friends, you have a soil having some weight, and it is for all practical purposes considered to be homogeneous, isotropic whenever possible. But in this case, at least we consider it to be homogeneous. And then we decide the depth at which the foundation is to be put. And that has to be decided based on several aspects, mainly the geotechnical aspects. And once we decide on that, we will have the excavation made. Of course, before that, soil will have some stress in this. What is the stress? The stress will be the weight of the soil here. Now, you build your structure, and that structure will carry some weight. Due to that, the stresses here will be much more than what was the stress before. It will carry much bigger stress. And we'll have to find out this stress, which later I show you, we call it as contact pressure. And this stress should be within limits. And what limit? We'll try to see now. We'll try to see in the lecture which follows now. So we have a few terminologies which we need to consider. One is ultimate bearing capacity. Ultimate itself shows that, it is the maximum value. Bearing capacity, it is the capacity of the soil to bear that ultimate load, ultimate stress. I use the symbol QF to represent this. So it is the maximum pressure which the soil here can take, where just below the foundation, before it fails. All failures in soil is shear failure. Here also the failure will be shear failure. So ultimate bearing capacity, QF, is equal to the maximum force divided by area at which soil still does not fail, or any further force, there will be failure. We also use this terminology, net ultimate bearing capacity. What is net ultimate bearing capacity? Ultimate bearing capacity, the maximum load it can take. Net ultimate bearing capacity is maximum load minus whatever load it was taking before. That is the initial overburden pressure. So net ultimate bearing capacity, I have used the symbol Qn, will be equal to Qf minus initial overburden pressure Q naught. And if there is no surcharge which exists, then Q naught is equal to gamma times D or dF here. Then the terminology safe bearing capacity. This is very much used in the design office. One of the important parameters in the design of foundations, or I would like to say most important parameter. So QS is the symbol I have given. Sometimes we simply say SBC of soil. So QS is the safe extra load or extra pressure in addition to the existing overburden pressure the soil can withstand. So you have the existing overburden pressure, which we call it as Q naught here, plus you have the net bearing capacity, net ultimate bearing capacity, which is equal to Qf minus Q naught. Only for the net ultimate bearing capacity, you apply the factor of safety. That's why I call it as safe load. In addition to the overburden pressure. So it's always equal to the overburden pressure plus safe pressure. When I say safe pressure, safe net pressure is safe extra load divided by factor of safety. And usually, if nothing is given, you can assume a factor of safety of 3. And we use SBC very importantly for proportioning of a footing. If you know the design load, then knowing SBC, you can determine the area of the footing. It is one of the most common parameters for the design of foundations. We also use another terminology called allowable bearing pressure. I have symboled it as QA. Sometimes we call it as ABP. So this allowable bearing pressure, I say, is more superior to SBC in the design. So allowable bearing pressure takes into account not just the failure, it also takes into account the other aspect, settlement, keeping the settlement well within limits. So it is the safe extra pressure a ground can withstand, considering both shear failure and settlement criteria. Well, friends, whenever a load is applied onto the ground will be stressed. You keep on increasing the load, stresses in the ground increase till such time it fails. There are many factors which influence the stresses in the ground and the failure of the ground. One of the important factors is the mode of failure, mode of shear failure. So many researchers have worked on that. Wesik in 1973 is one of the first to have mentioned that there are 3 modes of shear failure you can think of in case of bearing capacity determination of ground. The 3 modes of failure are, one is general shear failure, the other one is local shear failure, and third one is punching shear failure. We'll try to see what are these and how we have to take into account in our designs. So in this figure, I have on the left hand side a ground subjected to loads, and under the load the ground has failed. There are 3 cases I am showing here. A is one typical case where we say that the failure is of general shear failure type. C is the other extreme, which is called punching shear failure type. B is in between, which is called local shear failure. And the same thing, the load versus settlement. Whenever you apply the load, there will be settlement. you're going to measure the load or the stress and the settlement which is experienced by the ground or by the footing on compressible ground. So when you plot a graph between these two, you call it as load settlement curve or pressure settlement curve. And you notice that these are of three different types as seen here. So first one is called general shear failure. As you rightly see here, the failure surface is sufficiently large. Point number two, you can see that there will be bulging on either side of the foundation. And this bulging extends for sufficient length. And if you try to see the settlement is minimal. So this is almost on the verge of failure, and on the verge of failure, you can see a shear failure surface, something like this. And once the failure happens, the footing snaps, the footing experiences a rotation, which is very typical of either stiff clay or dense sand in or on shallow foundation. And in this case, you will be able to see some peak in the load settlement curve, and immediately after that, the settlement will be enormous. It continues to collapse. On the other hand, the other extreme punching shear failure is when the soil is in loose state. If it is clay soil, it is in a soft state. So when you apply the load, the soil, because it is loose, because its relative density is low, because it has the capacity to experience large amount of compression, it experiences settlement without any experience of bulging on the sides. The amount of settlement is also very large. So if you try to see the curves between load and settlement, you will notice that A is something like this, whereas C is gradual and continuous failure like this. Depending on the mode of failure, the capacity keeps changing, and it's one of the important things which has to be taken into account. As I said earlier, this is general shear failure. As soon as the failure happens, the footing rotates. You can approximately see a peak in the load settlement curve, and then it drops. And this is seen in very dense soils, also seen in shallow foundations. On the other hand, punching shear failure is one in which large amount of settlement continuously happens. You won't see a bulging like this in that case. So this is seen in very loose soils or soft clay. So I have given some of the information about what happens during general shear failure. You can see that there is a peak in the load settlement curve. Therefore, once you reach the peak, it will cause huge amount of damage. As I said earlier, there will be considerable bulging on either sides, and the amount of spread is large. It happens in dense soil, there will be a small settlement. The punching shear failure is extremely opposite to that. You don't see any peak value in the load settlement curve. It almost becomes vertical, indicating that, at small load, there will be huge amount of settlement. It experiences large settlement. Failure is not sudden, it is gradual. You will not see bulging or lateral spread on the sides of the foundation. And if you just look at the previous case here, this is the failure surface. the failure surface is very clear in general shear failure. On the other hand, failure surface is not so clear in local or punching shear failure. This type of failure is seen in loose or soft soil. I have tried to give the differences between these two. The important things, numerical values you should remember are general shear failures happen in a soil which has very large value of phi equal to 36 or more. In a soil which is stiff, therefore SPT N value will be always 30 or more. The relative density in case of granular soil will generally be more than 70%, and undrained shear strength CU will be more than 100 kilopascals. On the other hand, punching shear failure is seen in a soil which is loose, therefore phi will be 28 degrees or less. SPT N value is less than 5. Relative density is less than 20%. CU will be less than 50 kilopascals. So general shear failure experiences very small strain, 5% or so. On the other hand, local shear failure experiences very large strains of the magnitude of 20% and above. This was a graph plotted by Vesic to indicate the locations of general, local and punching shear failure in a graph plotted between relative density and the relative depth. You can notice that general shear failure happens here, wherein the soil is of relatively dense state. 2, the depth to width ratio is generally very small, less than 3 or so. Therefore, general shear failure is commonly seen in shallow foundations. It's also found in a soil which is stiff or dense. On the other hand, the punching shear failure is seen in all these soils. So significantly, punching shear failure is seen in a soil whose relative density is very low, 20% or so, and which has got deeper elevations, which has got depth to width ratio of 4 and above. Local shear failure comes in between. So as a summary, phi greater than 36 degrees, we call it as general shear failure. We don't apply any correction in the equations which we use. On the other hand, phi less than 28 degrees, we call as punching shear failure. In that case, we apply the correction. The correction is that, the cohesion should be taken as 2/3 of whatever cohesion is. Friction angle should be taken in such a way that tan phi of the system is equal to 2/3 of tan phi. It should be reduced. And accordingly, you find out phi dash. And phi dash is used to find NC, NQ, N gamma, which you call as NC prime, NQ prime, and N gamma prime. For phi value anywhere lying between 28 and 36 degrees, we just apply the, it's in the transition zone. Therefore, we try to interpolate, linearly interpolate. Friends, this is the equation which we have to remember for bearing capacity theory. QF for me is the ultimate bearing capacity. This is for strip footing. So it is derived considering plane strain idealization, and you get the expression something like this. So the derivation is done by considering limit equilibrium approach when the soil is at its plastic failure situation, and it's a semi-empirical method of analysis because somewhere you'll have to make certain intuitions, certain assumptions. So according to this theory, the equation has 3 parts. The first part is with respect to cohesion, which the soil in the neighborhood of the foundation experiences. The second part is mainly due to the surcharge on top. And third part is mainly due to the soil type. So N gamma term. So the density of the soil below the ground. So we say it is CNC plus gamma D NQ plus 0.5 gamma B N gamma. C stands for unit cohesion. NC, NQ, and gamma are called bearing capacity factors, which are simply functions of phi, functions of angle of internal friction. Gamma is the unit weight of soil. You can just consider the bulk unit weight at a place. B is the width of foundation, and D is the depth at which the foundation base is placed, depth of foundation. And how do you find NC, NQ, and gamma? These are all functions, direct functions of phi. Normally you have equations, you have graphs, you also have tables to determine them. So for various values of phi, it's a function of phi alone. You can find NC, NQ, and gamma. And with increase in phi, all these also keep increasing. According to Terzaghi's theory, when phi is 0, NC is 5.7, N gamma is 0, and NQ is equal to 1. On the other hand, when phi keeps increasing, you will notice that these values also keep increasing. That means denser the ground, more will be phi, more will be the value of NC, NQ, and gamma, and hence bearing capacity will be high. On the other hand, when the ground is loose, phi is less, correspondingly NC, NQ, and gamma are less, therefore bearing capacity also will be less. So this is Terzaghi's bearing capacity factor. And in case you have phi less than 28 degrees, you are required to reduce the shear parameters. Instead of C, you put C prime, which is 2/3 of C. Instead of tan phi, you put 2/3 of tan phi. And hence, the bearing capacity which you calculate for a soil with low values of phi will further be reduced. You apply that reduction. Friends, you remember net ultimate bearing capacity. Ultimate bearing capacity is QF, which is given by the three terms. Net ultimate bearing capacity is QF minus gamma D. So after putting that, I get the equation something like this. So instead of NQ, you're going to use NQ minus 1. Likewise, safe bearing capacity is this net ultimate bearing capacity divided by whatever factor of safety you put, plus the initial overburden pressure, which is equal to gamma D whenever there is no surcharge. So if nothing is given, you can use a factor of safety of 3. But these days, factor of safety of 2, 2.5 are also used. There are many factors on which this bearing capacity theory depends. One, of course, the type or mode of failure I mentioned. The other important factor is shape. You notice that the 3 shape factors, the first term is cohesion related, the second term is surcharge related, and the third term is the density related. So SC, SQ, S gamma are equal to 1 for stiff footing. Therefore, the same equation, QF is equal to CNC plus gamma D and Q plus 0.5 gamma B and gamma holds good. On the other hand, if you use square, rounded, or rectangular ones, this is how the equation slightly changes. It takes into account the geometry. So, friends, circular footing, QF is going to be 1.3 times CNC plus gamma D and Q. And please note, instead of 0.5, it is 0.3 gamma B and gamma. On the other hand, square footing, the only difference is in the third term here. It is 0.4 gamma B and gamma. And if you take a stiff footing, you should know that these shape factors are dependent on the size of the stiff footing. Rectangular footing. So it is 1 plus 0.3 B by L into CNC plus gamma D and Q plus 1 minus 0.2 B by L into 0.5 gamma B and gamma. So if it is stiff footing, you will notice that B is small compared to L. So B can even be 0 and L will be enormous. So this is rectangular footing. The other effect which I want you to remember, or which I want you to consider, is water table effect. Always we say water table or presence of water is dangerous to soil. It is the worst enemy to soil. So it can cause all kinds of problems, including failures, large settlements, and so on. So Terzaghi gave an expression for considering the correction, considering the presence of water table. So he used this in the second and third terms, which is called as RW1 and RW2. These are called coefficient to reduce the bearing capacity due to the presence of groundwater table. So how do you find RW1, RW2? So RW1 is the second term, which is mainly due to the overburden in the neighborhood. RW2 is the third term, which is mainly into this portion. So let us take this into account. So RW1 is in a very simple linear interpolation, is determined like this, where D is the depth. ZW1 is the depth from ground surface to the point where the groundwater table exists. So you should know that RW1 will always be between 0.5 and 1. When the water table is at the ground surface, RW1 will be at its lowest, 0.5. When the water table is below the base of the foundation, or even at the base of the foundation, RW1 is equal to 0.5. Anywhere in between the ground surface and at depth, RW1 equal to anywhere between the ground surface and the base of the foundation, RW1 will range from 0.5 to 1. So this is the expression for RW1. So effect of RW1 is to reduce the bearing capacity. When will that happen? Whenever the groundwater table is high. So case 1, you will notice that the groundwater table is at the surface, therefore automatically ZW1 will become 0, and accordingly you will notice that RW1 will be 0.5. On the other hand, in case 2, when the groundwater table is at a depth in between the top surface and the base, RW1 is between 0.5 and 1. And the third case is when the groundwater table is at the base or below the base. Automatically ZW1 will be equal to D or more. Therefore, RW1 will be 1. So take the case when the groundwater table is much, much beyond, then also RW1 will be equal to 1. Then RW2 determination requires the measurements made to the groundwater table, to the surface of groundwater table from the base of the foundation. It's not from the ground surface, but from the base of the foundation. And you will notice that this value, which we call as ZW2, will range from anywhere here where ZW2 is 0 to a great value. But you will notice that whenever this influence zone exceeds a depth beyond the width of the foundation, you don't have to worry. You can simply say that it is groundwater table is at deep elevation. So you don't have to take the effect of groundwater table. So friends, therefore, RW2 also ranges between 0.5 and 1. So it is basically measured from the base of the foundation till the groundwater table level. When the water table is at the base of the foundation, the value is 0.5. When the water table is at a depth B or beyond the base of the foundation, RW2 is equal to 1. Any intermediate value, RW2 will lie between 0.5 and 1. So whenever groundwater table is either at the base or at the top, you will notice that RW2 is 0.5. On the other hand, whenever the groundwater table is at the base, here also RW2 is 0.5. But if it is at some depth below the base of the foundation, you will notice that RW2 lies between 0.5 and 1. And when the groundwater table is below the foundation base and beyond B, at a point much beyond B, you will notice that there is no effect of the groundwater table, and hence RW2 is equal to 1. So we use simple interpolation equations to determine RW1 and RW2. The value range is between 0.5 and 1 for that. The other important function or factor we have to consider is eccentricity in loading condition. It is always assumed that the load is concentric, and hence, load is distributed evenly on the foundation. Therefore, the reactions from the ground also is even. Just imagine a situation when the distribution is not even, and when the load is applied not concentrically but eccentrically, things are going to be different. So let us try to see how it is taken into account. For instance, you have the foundation and you have the load. If the load is central, automatically the resultant also passes through the center, through the CG of the load. And hence the distribution at the base will be uniform. On the other hand, if the resultant of the force is not along the centroid, you will notice that resultant will be shifted a little away. Therefore, you have to find out the eccentricity by which it has shifted. Once you know this eccentricity, then you need to consider the effective width only, which I call as B dash, which is equal to the actual width minus 2 times E. This is what you have to take into account. And hence, a footing can be eccentric when the resultant is shifted beyond the CG, when there is a moment in addition to force, and in one or both the directions, you can find the eccentricity. But here, we will restrict our talks to only when eccentricity is only along one direction. So you consider a situation when you have the footing in plan like this. The centroid of the footing is here. The load, resultant of the load also is supposed to be here, but due to some reason, the resultant is shifted by some quantity called E or Ex here. So it is presumed that once it is equal to Ex, then 2 times Ex will not be acting, and hence only the width you have to consider is this one, which is equal to, say, B dash, and B dash is equal to total B minus 2 times E. So in all your calculations of bearing capacity, you need to consider the equivalent B, and whenever eccentricity is in both the directions, it will be something like this. Therefore, though you provide this much foundation, only a part of the foundation is expected to act. That means you are going to reduce the area of cross section. On the other hand, the effect of eccentricity is to reduce the bearing capacity. Terzaghi's equation I already gave you, very classical work, 1943. And later on, many investigators worked on bearing capacity problems. And even now you can see a lot of research going on. And then one such work is by Meyerhoff. So Meyerhoff, Bala, several people, work together and call this as general bearing capacity theory, your equation. Accordingly, you need to consider the different factors influencing the bearing capacity. Like before, you have the 3 terms. The first one is cohesion term, second one is the overburden term, the third one is sorry, sir. Yeah, I'm in a class. I'll take your call later on. Okay. So 3 terms, and hence the only additional things here are you try to take the effects of shape, depth, and the other one is inclination of the load. So shape effect in Terzaghi's theory, I gave you the coefficients which you need to consider for different shapes like square, rectangle, as well as circular. But here is a general bearing capacity theory considering not only the shape effect, but also the depth effect and the other situation when you don't consider the load to be concentric, load to be vertical, when the load is inclined. It can happen because you also need to consider the horizontal load. Therefore, resultant can be inclined. So in that case, you consider these coefficients S, D, I. For the first term, the suffix used is C because it is related to cohesion. For the second term, it is Q related to surcharge. Third term, it is related to gamma because we are talking about the ground below the foundation. So Meyerhoff did a lot of work and he gave this equation and gave equations also for the bearing capacity factors NC and Q and gamma as shown here. And SC, SQ, S gamma are shape factors, DC, DQ, D gamma are called depth factors. Likewise, IC, IQ, I gamma are called the load inclination factor. And this table gives the values of shape, depth, and load inclination factors for different phis. So here C is cohesion, gamma is unit weight of soil, D is the depth of the footing, B and L are width and length of footing, and you find out Kp, the coefficient of passive earth pressure, alpha, angle of the load with respect to the vertical. Friends, again, I stress that, you should remember these terminologies because normally, a problem related to bearing capacity theory will have huge amount of, words in the question. That means, you'll have to read several times the question. And sometimes they will ask ultimate bearing capacity, sometimes they will ask net ultimate bearing capacity and so on. So I want you to remember this. Ultimate bearing capacity I have symbolized as QF. Net ultimate bearing capacity I have symbolized as QN or QNF, which is equal to QF minus overburden pressure. If the ground is level, then it is gamma D. QS is the safe bearing capacity, which is equal to net ultimate bearing capacity divided by factor of safety plus extra pressure. There is also net safe bearing capacity, which is equal to QS minus gamma D or this value alone. I want you to be clear. So there are a number of questions which are asked. I read out the questions. A 3 meter wide stiff footing, please note stiff footing, width is 3 meters, is founded at a depth of 2 meters below the ground surface in a C5 soil. Water table is at 5 meter depth. So basically 5 meters is beyond the scope. You can neglect the effect of water table. Soil properties are given, C is given, phi is given, gamma sat is given, gamma bulk is given. And gamma W of course is given. The values of bearing capacity factors are shown here. And using Terzaghi's theory, applying a factor of safety of 2.5, you need to determine the safe bearing capacity of soil. And 4 choices are given. So you will notice that this is the equation you have to use because it is stiff footing. And for safe bearing capacity, ultimate bearing capacity minus gamma D divided by factor of safety plus gamma D. Since phi is less than 28 degrees, if you see here, phi is equal to 26 degrees, less than 28 degrees, the type of failure is local shear failure. And whenever it is local shear failure, you have to reduce the shear parameters by 2/3. So instead of C, it becomes C prime, which is equal to 2/3 of C. Instead of tan phi, it becomes tan phi prime, wherein, tan phi is equal to 2/3 of tan phi prime. So that's how you reduce the shear values and all other things are given. Find out the bearing capacity and find out the safe bearing capacity And you will notice that this is the answer you will get. The nearest answer is B, and hence you know it is acceptable. The next question is a square footing 2 meters wide is placed at a depth of 1 meter in a sand deposit. Please note sand deposit. That means C is 0. Dry unit weight of sand is given 16 kilonewton per meter cube. This footing has an ultimate bearing capacity of 800 kilopascal. So QF is given. The depth factors dQ, d gamma are 1. You don't need to take that effect. Bearing capacity factor N gamma is 20. So what you are required to find is the, you have a new footing whose side is 3 meters, depth is 2 meters. And for a factor of safety of 3, you have to find out SBC of the new foundation. Please note that SBC is not a unique value. It depends on the shape of the foundation, size of the foundation, and many other things. So in this case, I have the equation for strip footing. 2 meters wide, square footing is there. Therefore, I need to apply the square footings equation. That is 1.3 CNC plus gamma D and Q plus 0.4 gamma P and gamma. And then, because C is 0, this term vanishes. I know N gamma, I know QF, and hence I find out NQ. That's what I have done here. And once I know NQ for the first foundation, the second foundation, the width is given as 3 meters, depth is given as 2 meters, and factor of safety is given as 3 meters. For this, you find out the SBC. It's come to 510. That's what we'll be putting here. Likewise, you have the third question. Square footing, 2 meter by 2 meter, is subjected to inclined load in this case. The load is inclined by an angle alpha equal to 20 degrees. Water table is located well below the foundation. You don't have to take its effect. Considering one-way eccentricity, the net safe bearing capacity of the soil when factor of safety is 3 is so many kilonewtons. Bearing capacity factors NQ, N gamma are given. C is 0, therefore NC is of irrelevance. Shear factor, they have called it by as FQS and F gamma S. Okay. And so on. Depth factors are given as FQD, F gamma D. Inclination factors are given as FQI, F gamma I, and so on. So I have put all these values, and what I am required to find is the net safe bearing capacity. Net safe bearing capacity is safe bearing capacity minus gamma D, ultimate bearing capacity minus gamma D divided by factor of safety. All things known, I only need to determine the value of ultimate bearing capacity and substitute here. So I calculated everything, but I have missed out to find the final value here. So just substitute the relevant data here. Likewise, there are many questions, I will probably go to these questions later on. Maybe I'll just try to answer one last question. Net ultimate bearing capacity of a footing embedded in clay stratum dash. Choices are given. Please note, net ultimate bearing capacity. So when I say bearing capacity, this is the equation. Net ultimate bearing capacity is this minus gamma D. So that's equal to CNC plus gamma D into NQ minus 1 plus 0.5 gamma B N gamma. So what does it do? Does it increase with depth of footing only? Or does it increase with size of footing only? Or does it increase both with depth and size of footing? Or is it independent of depth and size of footing? Please note here, the catch is what type of soil here it is. The moment it is clay soil, you will notice that, only C exists. NQ will be 1, and when you take net ultimate bearing capacity, NQ minus 1 will be 0. and n gamma is 0. Therefore, second and third term vanish, and only Q will be C and C, which is both independent of depth as well as size. Therefore, answer is D. I go to these questions little later on if I have time. I just proceed further. I have a number of, okay, maybe I just take this question number 12. 4 columns of a building are located within a plot size of 10 meter by 10 meter. Plot 10 meter by 10 meter. And then 4 columns are there like this. The expected load on each of the column is 4,000 kilonewtons. Allowable bearing capacity, ABP or SBC, is 100 kilopascals, 100 kilonewton per meter square. What type of foundation do you suggest for it? Please note, plot size is 10 into 10, 100 square meters. Each individual foundation requires, with an SBC of 100 square meters, for 4,000 kilonewtons requires 40 square meters. There are 4 such columns. 4 into 40, 160 square meter, which is greater than 100 square meters. So you can't definitely have isolated footing. You can't either have raft foundation. The only choice is to go for a deep foundation, that's pile foundation. Therefore, answer is C. So I go further. The types of foundation. Okay, broadly, foundation is classified into 2 types, shallow and deep. A shallow foundation is one whose depth is smaller than the width. A shallow foundation generally assumes that the neighboring soil does not exist. That means the entire load is transferred at the base. Given a choice, you should go for shallow foundation. These are some of the typical shallow foundations. On the other hand, a deep foundation is one in which the depth is much, much greater than the width of foundation. D by B ratio will be 5 or more than 5. And in deep foundations, you not only consider the load carrying capacity at the base, which you call as tip resistance, but also consider in the neighborhood. Pile and well foundation are the popular deep foundations. So shallow foundation is one in which the load from the superstructure is not extraordinary. Basically, it is small. Plus the soil in the neighborhood, shallow depths, is having sufficiently good bearing capacity. Under that situation, you go for shallow foundation. On the other hand, you go for deep foundations when the foundation is deep, taken through a weak soil into hard rock or bedrock. And in deep foundations, automatically the load from the structure will be high and soil near the surface will be weaker. These are typical shallow foundations. Isolated footing, very common one, used for one single column, one footing for one column. If you combine 2 columns together and put one single foundation, it is called combined footing. Sometimes you can go for strap footing when you provide 2 separate foundations and then a beam, a rigid beam connecting these 2. Strip footing is one in which, you have a number of columns in a row connected together. If they are in different rows, then, you go for raft foundation, which is a complete solution. Well, I just tried to mention earlier also, proportioning a foundation requires the knowledge of SBC or allowable bearing pressure of soil. So if I have a load of 1000 kilonewtons, if I know the, if I put a foundation of some area, say 1 meter by 1 meter, the soil here will be subjected to stress equal to 1000 by 1 square meter. That is 1000 kilonewton per meter square or kilopascal. If I want to reduce the stress here, I need to increase the area. So instead of 1 meter by 1 meter, if I provide a 2 meter by 2 meter footing, then the stress will be 1/4 of that 250 kilonewton per meter square. So depending on what is the stress which is permissible at that place, you decide to proportion the foundation, which is important. Very quickly into combined footing. As I said earlier, whenever you have a footing in which, two columns are connected together and you have one single foundation, you call it as combined footing. You provide a combined footing under these conditions. It is preferable to go for isolated footing. Only when it is not possible to go for isolated footing, you go for combined footing, which is more costly. The cost is mainly due to the cost of the shear reinforcement in the form of, rings in the foundation. So one of the important reasons why you go for combined footing is the property line restriction. The other important reason is when the columns are closely spaced, when the columns are heavily loaded, when SBC of the soil is low, that is when the stresses can overlap. You also go for combined footing when you have scare of differential settlement, or when you believe the structure is very important, you don't want to take any risk. Sometimes, based on designer's wish, also you provide the combined footing. I skip the discussions on this and go further. If there is time, I'll be happy to talk about it later on. Raft is a complete shallow foundation. Whenever you have a raft foundation, you can say that, the structure is going to be very stable. And you go for raft foundation under these conditions, when there is a property line restriction, when there is a possibility of overlap of stresses, scare of differential settlement, whenever the structure is important, at the time when the designer decides for his convenience, groundwater table is fluctuating and it is near the surface, you have cellar floor, and you have restriction due to settlement. Under these situations, you go for raft foundation. Please note that raft is very expensive. It is the costliest of shallow foundations, and you will avoid wherever possible. But when you provide a raft foundation, it is more robust. You go for raft foundation whenever there is settlement criteria, whenever you feel that the settlement is beyond limits and hence you want to reduce, or when more than 50% area is covered by the foundation, then also you go for raft foundation. A simple thumb rule, in case you want to increase the number of floors, you go deeper. You just have one basement floor, which is equal to 3 meters. And if you provide one basement floor like this, you may be in a position to put 3 additional floors. So whenever you want to increase the number of stories, you may go for raft foundation. Quickly onto contact pressure. Contact pressure is the pressure which you see or which is experienced by the soil exactly below the foundation. So in a very simple way, contact pressure is equal to load divided by area of the foundation. Please note that contact pressure depends upon the rigidity of the footing, whether it is rigid or flexible. It depends upon the type of soil, whether it is a granular soil or cohesive soil. And when you go deeper into the foundation, because of depth of embedment, the contact pressure becomes more or less uniform. So you notice that the major difference between a rigid footing and flexible footing in terms of contact pressure is, in rigid footing, contact pressure is never uniform. On the other hand, in flexible footing, contact pressure is uniform, but the footing experiences settlement which is uneven. Then, depending on type of foundation, type of soil, on the other hand, the contact pressure changes. In granular soil, you should always know that in this granular soil, sandy soil, contact pressure will be maximum at the center because of the effects of confinement. And at the edge, it will be close to 0. On the other hand, in a cohesive soil like clay soil, due to the edge stresses, the contact pressure will be maximum near the edges and it will be minimum near the center. I go on to the other aspect, settlements. Please note that settlement is a very important phenomenon which has to be taken into account. Whenever you have a structure subjected to load, the load gets transferred onto the soil, which is compressible. And depending on the stresses experienced by the compressible soil, the soil will collapse. Soil will experience a vertically downward movement. And hence the structure also moves vertically downwards. This vertically downward movement of the structure is called settlement. If it is uniform, then maybe the structure won't fail. But it will have a lot of serviceability problems. On the other hand, if it is non-uniform, quite likely that the structure may fail, which we have to take into account. So, with time, for various reasons, soil experience movement, and remember, the settlement can be divided into three components. SI, which is immediate or elastic settlement. SC, which is consolidation settlement. And SS, which is secondary settlement. The first settlement which happens is the immediate settlement, which happens in about 15-20 days after the load is put, after the structure is built. And after that, consolidation settlement may or may not happen depending on the type of soil, depending on the saturation level of the soil. And then the secondary settlement happens later, very much later. So, friends, I would like you to remember a few formulae here. Immediate settlement, as the name itself says, it is the settlement which happens immediately. It is also called elastic settlement. And hence, to compute this, you use elastic theory. So, elastic constants. It is experienced by all types of soils. So, it all depends upon the elastic constants. And the formula which you need to use is this. I want you to remember this. So it's equal to SI equals 1 minus mu squared by E. So this bracketed term is the elastic property of the soil, multiplied by Q. Q is the contact pressure, multiplied by B, width of foundation. And I rho is called influence factor. So I want you people to remember this equation wherein E stands for Young's modulus of soil, mu stands for Poisson's ratio, Q is the contact pressure, B is the width, and I rho is the influence factor, which depends upon the rigidity and shape of the foundation. There are a number of questions. This question is so long, but you are required to find here the immediate settlement. Please note, immediate settlement. The values are given. This is the equation which you have to remember. In immediate settlement, you require mu, you require E. Mu and E of soil. Please note, mu stands for Poisson's ratio. E stands for Young's modulus of elasticity of soil. And Q is the contact pressure, which is equal to load divided by area. B is the width, and I rho is called influence factor, which depends on two things, rigidity and shape of the foundation. And in this case, all values are given, including I rho. I rho is given as 2. I have written here as IF, that's given as 2. So E is known, it is given in MPa, I have put it in KPa. Q is known, B is known, mu is known. Therefore, you find out immediate settlement, which happens to be 0.0182 meters. Exactly similar is this question. You have a circular raft. So B is going to be 20 meters diameter, 1.6 meters thick, which is provided for a tank that applies a bearing pressure of 110 kilopascals. Therefore, 110 kilopascals is the contact pressure. Okay, Q. In sandy soil, having Young's modulus 30 MPa or 30,000 kPa and Poisson's ratio mu equal to 0.3. Raft is made of concrete. Raft values are given large number of times, in geotechnical engineering. Unnecessary data are given, don't get confused. Considering this raft as rigid, elastic settlement is given by any of these three. So you will notice that it is equal to 66.71. So formula is here. Q is given 110. B is the width, 20 meters. E is the Young's modulus of soil. Please note that is equal to 30,000 kPa. Mu is the Poisson's ratio of soil, again 0.3. Substitute here and you will get the answer. So the right answer is D. Consolidation settlement happens due to consolidation. All of you know the process of consolidation, which generally is in vulnerable clay soil. Because of the expulsion of water, consolidation happens, and it's a long-term process. I'm not going into the theory of this, but never get confused between compaction and consolidation. Both of them experience volume change, in fact, volume reduction. Compaction is a mechanical process in which volume reduction is due to the expulsion of air. On the other hand, consolidation is due to the expulsion of water. So consolidation can happen only in saturated clay, whereas compaction can happen in a partially saturated soil. I'll not go deep into this, and I want you to remember this equation. SC, consolidation settlement, is equal to, please note, CC by 1 plus E naught. CC happens to be compression index, which you obtain from consolidation test. E naught is the initial void ratio, and H is the thickness of clay layer. Then please note, it is clay only. You don't consider sand because sand does not experience consolidation. Log to base 10 of, please note, sigma naught dash we use, but here I have just put sigma naught. Okay, it is the effective initial confining pressure or effective initial overburden pressure at the middle of clay layer. And delta sigma is again at the middle of the clay layer, the extra pressure which is going to happen due to the new construction. So the problem is given here. First of all, I want you to put the formula and then read the problem at least twice and see the sketch. A water tank is constructed on a soil deposit shown in figure below. A circular footing 3 meters in diameter. Depth of embedment 1 meter. Okay, has been designed to support the tank. The total vertical load to be taken by the footing is 1500 kilonewtons. So vertical load is 1500 kilonewtons. Assume unit weight of soil, unit weight of water as 10 kilonewton per meter cube, and load from the base of the foundation disperses. Load dispersion can be considered to be 2 vertical to 1 horizontal. So you are required to find the expected settlement. CC is given here. You see here, silty sand, sand, dense sand. None of them experience consolidation settlement. Only normally consolidated clay is there for a thickness of 10 meters. That is what experiences consolidation. So CC is known here, given 0.3. E naught is the initial void ratio, which is also given. H is the thickness, which is 10 meters. Sigma naught dash is the effective confining pressure at the middle of clay layer. So 5 meters of clay layer, you consider on top 6 meters of sand and 1 meter of silty sand. So all these are considered to find the effective stress here. And del sigma is the effect of new construction. So at this point, it is 1500. But load disperses at 2 vertical to 1 horizontal. And hence, you will get del sigma value based on this 1500.78 pi by 4 into. So this one is 3 meters and then, 6 meters on this side, 6 meters on this side, totally 15 meters. That's what is considered. So You compute the value and you find that the value is close to 53.226. So likewise, I also have another problem. All data given, you can read through here, write down the expression. I want you to by heart this, and CC is equal to 0.6 here. You can read from here. E naught is equal to 1.3, which is given here. H is the thickness of the clay layer, which is given. And it's also mentioned that the increase in the vertical pressure due to the new structure, foundation, is equal to the existing overburden pressure. So sigma naught dash plus del sigma will be equal to 2 times sigma naught dash. Denominator is sigma naught dash. Therefore, this entire expression is equal to 2, and hence you compute SC. So friends, here I want you also to know that coefficient of consolidation, CV, is given, but it is redundant. Many a times in geotechnical engineering problems, you are given some data which is not relevant, and here SC you find out equal to 0.314 meter, but when expressed in millimeters, it will be 314 millimeter. Therefore, answer is B. You have a number of such problems you can keep on solving. And here you can see same expression I have used. Sand above, clay, 1 meter thick clay. Below that you have hard soil. It is this clay which experiences consolidation settlement. And I need to write down, see for example, that, okay, in this problem, see CC. So this is a slightly tricky problem. Okay. So you are not given E naught directly. E naught is the initial void ratio. It is not given directly. You are knowing the natural water content. You know the specific gravity of clay. Degree of saturation has to be 100% if it is consolidation. S is equal to 1. Therefore, WG equal to SE you use, and hence E void ratio is determined. To find CC, you have CC here, compression index of clay and recompression index of clay. You'll have to check which one to use. What is recompression? When it is unloaded and reloaded. So for that, you are given the pre-consolidation pressure. Pre-consolidation pressure at the middle of clay layer is 60 kilopascal. And in this case, you will notice that the load applied, compacted fill, okay, is 2.5 meters height on top for a unit weight equal to 20, plus, the earlier overburden pressure will be more than 60 kilopascal. If that is the case, the present pressure is much more than that, and hence, you have to apply the compression index, not the recompression index. Whenever the present pressure is less, okay, it is not the virgin curve, compression curve. You'll have to use recompression curve, and you compute the values. I just go on to the next, portion, that is the secondary consolidation. So far, I did not see any question on this. Secondary consolidation is also called creep consolidation. It is seen in, some organic soils or very sensitive clayey soils. This happens after complete consolidation is over. That means, whatever excess pore water pressure is in the soil, that dissipates. Even today, it's a question mark about how this happens. But definitely it is due to the redistribution of the particles in the long run under a sustained loading. And creep settlement continues and continues. Most of the times we consider the lifespan of the structure for computing creep settlement. And it should be beyond the secondary or beyond the consolidation settlement. So you use this formula to find out that. Okay. So C alpha is the coefficient of secondary compression, H is the thickness. T secondary is time taken for the secondary completion, secondary settlement to be, consideration of that to be stopped. That means, till the lifespan of the structure. T prime represents the time taken for primary consolidation to be over. So, friends, with this, I go to pile foundations. If there is still Yeah, friends, sorry for the inconvenience. Always, we depend on network, and there was some problem with the network. So I apologize for the error there. So I just go back, and I'm not sure when the problem started, but anyway, I was talking about pile foundation. Pile foundation is a deep foundation. It's one of the very important types of foundations. Given a choice, you always go for shallow foundation. But when you don't have a choice, you need to go for deep foundation, like pile foundation. When do you go for pile foundation? Two important situations. Number one, the load from the structure is very heavy. So structure carries extremely heavy load, which the soil at the surface cannot bear. Two, soil near the surface is extremely weak. So in that case, you go deeper, you may find better soil. So you go to that depth at which you have firm soil. So you transfer all the loads from the structure through weak soil to stronger base. So two types of pile foundation based on the construction procedure. Bored pile is one in which you make a bore hole first, put the reinforcement cage, and then put concrete. Driven pile is one in which you drive a pile exactly the same way as you drive a nail into the wall. It will have a sharp edge at the bottom for smooth penetration. It will have a helmet or stronger top, so that when you hammer with a huge hammer, the pile head does not get damaged. So you drive it till the desired length. You can classify in different ways. One other classification of piles is based on the load carrying mechanism. You can call it as end bearing pile when the entire load is supported at the base, at the top, at the bottom. That can happen when the neighboring soil is weak. You also call it as socketed pile because it's like the pile is socketed into the hard rock or hard soil. On the other hand, friction pile, when the resistance is offered due to the skin friction between the pile and the neighboring soil. This is also called floating pile. In this case, you assume that the end bearing is negligible, very small, because cross-sectional area is small, and the load carrying capacity here, the bearing capacity here is also low. But these are the two extreme situations. In a normal circumstance, both of these exist. So you have both the friction resistance as well as end bearing resistance. So total load P is partially carried by the frictional resistance and partially at the base. P P is equal to P1 plus P2. And hence, I just call it as point resistance at the base as P, and here it is the shaft resistance along the surface as S. So ultimate load Q is equal to QP plus QS. So QS is the side friction component, QP is the, normally when you apply the load, firstly the load is carried at the base. Slowly it is transferred to the skin, surface resistance. And surface resistance slowly starts from top and then goes to the bottom. So until then, the shear here will not be mobilized. It takes some time. It takes some time for the disturbed soil to regain the strength. So typically, we consider the load transfer mechanism to be something like this. Initially at the tip, and then the surface resistance starts from top and gradually goes towards the bottom. So remember, pile capacity is, Q ultimate equal to QP plus QS. QP happens to be the capacity at the base. QS happens to be capacity along the shaft. This is the static formula which we use for that. That's exactly what is mentioned: skin friction plus end bearing resistance. And I have tried to derive here in a very simple way. The pile capacity Q is equal to QS, which is the shaft resistance, plus QP, which is the base, point resistance at the base. And QS is small QS, the stress, allowable stress in that, multiplied by cross-sectional area AS. On the other hand, QP is the stress or bearing capacity multiplied by AP. Q happens to be the total capacity. So QS is the maximum stress which the soil can bear, and QP is the maximum stress that the soil can bear at the base. And in cohesive soils, QS is equal to alpha times Cu, where Cu happens to be the undrained cohesion. Alpha is called shear mobilizing factor, which is 1 or less than 1. In a very stiff soil, that value will be very low. It could be even 0.15, 0.2, 0.3 like that. In soft clay, alpha will be close to 1. And small QP happens to be the bearing capacity. So whenever we are talking about bearing capacity, we will be interested in the first term here, that is equal to Cu into Nc. And for all practical purposes, you can take Nc value to be 9. On the other hand, in cohesion-less soils, you need to consider the confining pressure. So confining pressure or lateral pressure will be equal to K times the vertical pressure. And that K, you can consider K naught condition, because the soil is considered to be have experienced no strain. Under no strain condition, you can consider K naught, and the vertical stress will be 0 at the surface and maximum at the bottom. You take the average. That's why it is gamma length by 2, and K naught into gamma length by 2 is the horizontal stress normal to the pile near the surface, multiplied by the friction angle between the pile and the shaft, pile and the soil. So that's equal to, say, tan delta, where delta is either equal to phi, angle of internal friction, or less than that. So you can find out QS that way in cohesionless soils. QP, depending on the type of the soil, you can apply your bearing capacity equation, and C is 0. You don't consider the overburden effect. Therefore, it is 0.4 gamma Bn gamma for square footing, 0.3 gamma Bn gamma for circular footing. So this is shear mobilization factor, which is, either close to 100%, or sometimes, even 20% and so on. And the mobilization happens quickly in a soft soil. On the other hand, in a stiff soil, it takes long time. You also determine the capacity of the pile based on the dynamic formula. I told you that most of the times, we have driven piles. You have bored piles also, which generally run for a smaller length, smaller depth. You have had to make a borehole there, but more popular one is the driven pile. You use mechanical hammers. So you will be able to know the resistance depending on how much effort is put for penetrating the pile. So if you can try to compare the resistance of the energy to work done, you will be in a position to approximate the pile capacity. So you have few popular methods of determining the dynamic formula. The pile capacity using dynamic formula. One very popular one is called engineering news formula, which way back in the 19th century was given by Wellington. According to this, W into H happened to be the energy input, weight of the hammer dropped from a height. S happens to be the amount of penetration you see in the last number of blows. You take the average value. C happens to be some constant. So allowable Q will be equal to the ultimate Q divided by factor of safety. Because of lots of uncertainties involved, you choose a very high factor of safety of 6 and you find out the capacity. In Indian standard codes, Hiley's formula is used accordingly. This is the formula. It is more involved. It takes into account the efficiency of the hammer, efficiency of the blow. It considers the effect of the soil, effect of the helmet and several things, effect of the pile and so on. Therefore, it is more involved and you can find out the pile capacity also from Hiley's formula. There are a number of comments on dynamic formula, but the biggest advantage is that you use the formula to determine the in driven piles you are anyway going to drive the pile. So while driving the pile, you try to find out how much resistance was offered, and accordingly you do this. So piles are never put singly. Piles always are in group, and whenever you take piles in group, you will have to consider the efficiency, because when piles are in group, the total capacity is not equal to individual capacity multiplied by number of piles. It is much less than that, especially for floating piles, especially for piles wherein the frictional component is taken. And it's important for us to determine the group efficiency, which is less than 100%. So piles are generally put in different orders like this, and you have formulae to determine the efficiency. And I always like the Feld's rule, according to which 1/16 of the efficiency is lost due to the neighboring pile. You also need to consider negative skin friction, which can happen in filled up soil, organic soil, when the groundwater table recedes continuously, when the soil is highly compressible, and when you have heavy surcharge. So negative skin friction definitely is very dangerous, and load carrying capacity reduces because of that. Pile load test is very similar to plate load test, and you try to determine how much is the capacity of pile. So it is done either on the working pile, which will be used later on as a pile foundation, or on a test pile. So pile load test can be conducted both by gravity loading as well as reaction loading, and load settlement curve is plotted. So I'm going to stop here because it is time now. I would have really enjoyed solving a few problems here, but anyway, I only want to mention to you that this is a vast and very important subject. Lot of questions do come from foundations, especially shallow foundations. Also, there are questions which I have seen on settlements. So keeping that in mind, I want you people to prepare well. And this lecture will definitely be useful for you to understand the concept and solve as many problems as possible. I have tried to solve here, or I have actually considered several problems and solved. Please keep that in mind. And we at Vidyavardhaka College of Engineering want you people to study, prepare well, take the mock tests which we offer, or some other organizations also offer, practice well, and we want you to say that you enjoyed these lectures, and finally we want all of you to get selected through GATE for all your competitive future. I wish every one of you all the luck. I thank all my colleagues for taking lot of efforts, putting in lot of efforts for the successful training. I assure you that we come back next year also, and we will be with you. We will be able to, guide you in whatever way you want. You can talk to us by, contacting our website, and it will be a pleasure to interact with you, clarify our doubts, whatever way possible. So tomorrow, please take the mock test seriously, and we want you to have a lot of confidence. Thank you, everybody. And I also want to inform you at this point of time that we are planning to organize 4 more mock tests in January to prepare you people well. And we want you people to come back and take those mock tests. We are planning to give it on Sundays only. Therefore, you'll have no disturbance. So you can take those tests on Sundays. Good luck, and thank you, everybody.
Thank you, sir. Thank you, sir, for a wonderful session on the foundation engineering, covering the concept of shallow foundation, consolidation, and also the pile foundation. I request the participant to give the feedback. The feedback link has been posted in the comment box. Join the second session.